This is the beginning of the lecture on section 1.5, solution sets of linear systems. These notes are posted in Canvas. The zero vector is denoted 0 with a line on top when I write by hand. This would be a boldface 0 in the textbook. In R2, the zero vector has two components of 0, 0. In R3, the zero vector is 0, 0, 0, so on and so forth. So just be aware that when we use this zero vector notation, you need to know what dimension you're in. That should always be clear from the context of the problem. A system of linear equations with corresponding vector equation ax equals b, in which b is the zero vector, is called homogeneous. Thus, for a homogeneous system, the matrix equation can be written as ax equals 0, where 0 is in Rm. That's assuming that A is an n by m matrix. So if A has m columns, this 0 is in Rm. A homogeneous system always has at least one solution, x equals 0. If you plug in the zero vector for x, A times a zero vector is going to give you a zero vector. But the solution vector, the solution zero vector, is in Rn. That matches the number of rows of A. This is called the trivial solution. If there are other solutions, they are called non-trivial. So a homogeneous system never is inconsistent, never has no solution. It either has just the trivial solution or it has additional solutions. From section 1.2, we can see that a homogeneous vector equation has a non-trivial solution if and only if the system has at least one free variable. If there are no free variables, then the trivial solution will be the only solution. So let's do an exercise here. And here is a homogeneous system of equations, x1 plus x2 plus 2x3 equals 0, 3x1 plus x2 minus 2x3 equals 0, minus x1 minus 2x2 minus 6x3 equals 0. And for this system, notice that the constants on the right-hand side of the equal sign are all 0. So the b vector is 0. That's what makes it a homogeneous system. Clearly, if I set x1 equal to 0, x2 equals 0, x3 equal to 0, that's a solution to the system. And again, that's what we call the trivial solution. So is there a non-trivial solution? And we're going to try to determine that. If yes, we're going to describe the general solution. And what's new now, from now on, we're always going to write the general solution to a system in vector form. So let's go ahead and work through this problem. We're going to work through it together. For this problem, I went ahead and wrote this ahead of time. We're going to write this in matrix form. So the matrix form will be A times X equals 0. Again, here my 0 is what our B is turning out to be in this system. And the matrix A consists of just the coefficients, the variables on the left-hand side. The solution vector x will have three components, an x1, x2, and an x3. And again, this 0 here just stands for the zeros on the right-hand side, the b vector. Notice that that's also a vector in R3. Since A is 3 by 3, both x and this 0 vector have three components. So to solve the system, we're going to set up the augmented matrix, where I just write down the columns of A, followed by the B vector in the last column. So that's all zeros here. And we're going to apply row operations to get the augmented matrix into reduced echelon form. So let's go ahead and apply these row operations. I already have a 1 in this upper left-hand position, so that's great. That's going to become a pivot. I want zeros below that 1. So I'm going to replace row 2 with row 2 minus 3 times row 1. And let's write down what we get. I'm going to write that down right below here. And of course row 1 stays the same, only row 2 is changing. I get 0. I get 1 minus 3 is negative 2. I get negative 2 minus 6 is negative 8. I get 0 minus 0 is 0. And I recopy. And now I want to get a 0 in this bottom position of the first column. So I'm going to replace row 3 with row 3 plus row 1. That will give me a 0. And let's see what we get. So I recopy 1, 1, 2, 0, 0, negative 2, negative 8, 0. I'm going to get 0. I'm just adding these two together, so I guess I'm going to get negative 1. I'm going to get negative 4, and then 0. Now, you might have been tempted to do these two row operations at the same time, and you actually can do that here, but I just want to give you a warning about that. If you're ever tempted to do two row operations at once, there's no guarantee that always works. The only way to know that always works is you have to convince yourself that you would get the same results if you did the two row operations separately. So we did them separately here. This is what we got. If I did them at the same time, I would still just have this matrix here. So here it is okay to do these two row operations at the same time. But if you experiment with this, just again, check. Like I've seen students make a mistake where they try to do two row operations at the same time, and they don't get the same result if they do them separately. And in that case, it's not allowed. You can't do it. Really, row operations are performed one at a time. You can only take a shortcut if you're absolutely convinced you will get the same result if you do them separately. Okay, so let's continue on here. Now I have my first column set up nicely. Now I'm looking at the second column. I want to get a 1 in this next pivot position here as I come down diagonally. So I'm going to take row 2 and I'm going to multiply by negative a half. And that's going to become 1, 1, 2, 0 stays the same. 0, 1, I guess I get 4, 0. 0, negative 1, negative 4, 0. And now I like how I got a pivot here and a pivot here. And now I want to get zeros below my second pivot. So I want this minus 1 to become a 0. So I'm going to take row 3 and replace it with, it looks like row 3 plus row 2. We'll get that to be a 0. And I have 1, 1, 2, 0, 0, 1, 4, 0, 0, 0, 0, 0. I get a row of zeros. Now I'm almost in reduced form. I'm in echelon form. But to be in reduced form, I need to get a 0 above my second pivot, 1. So I'm going to have to take row 1 and replace it with row 1 minus row 2. And I'm going to try to squeeze that in here on this piece of paper. I'm going to have, still going to have 1 here. Row 1 minus row 2 is 0. I'm going to have 2 minus 4 is negative 2, 0. 0, 1, 4, 0 stays the same, and my row of zeros stay the same. Okay, now I'm going to move on to another sheet of paper. Now, this is now in reduced form. Remember these columns, the first 3 columns correspond to the 3 variables. Because I have a pivot in the first 2 columns, but I don't have a pivot in the third, that x3 is going to be a free variable. So let me now write out the situation with the equations. I have x1 or x1 minus 2x3 equals 0. I have x2 plus 4x3 equals 0. And then my third equation is just 0 equals 0. It doesn't give me any additional information. I need to be aware that x3 is free in order to be able to write out the vector form now. Let's write out the vector form of the general solution. And you'll always have to do this from now on. We don't want to just have a set of equations here describing the solutions. So the vector form means I'm going to express a solution x that has components x1, x2, and x3. And I want to write each of those components with numbers and variables involving only constants and free variables. So I can't write x1 or x2 in my general solution. So I can take the equation x1 minus 2x3, solve for x1. x1 is equal to 2x3. I can take the second equation, solve for x2. x2 is equal to minus 4x3. And if I have a free variable, I just write it. Now notice that I have x3 as a factor in each one of these entries. So I can bring that out in front as a scalar times the column vector 2, negative 4, 1. And this is basically my general form. I want you to write the certain words here, though. What we're saying is x3 can actually be any real number at all, and we should say that. Where x3 is any real number. Because there are actually infinitely many possibilities for this general solution. Some people use a different letter other than x3 because there's no special meaning to that third variable occurring here. I could write just an like a letter A and say A is any real number or anything at all. In fact, the geometry of this is if we call v that vector 2, negative 4, 1, and imagine v sitting in R3, and I'm not drawing this real precisely, I'm just saying suppose v is in that position, then the set of all these solutions are all the scalar multiples of v. Do you see we have a line and a line of solutions in R3. So we'll talk more about the geometry of this as we go further in the course. And one of the solutions is 0, 0, 0, the origin. In fact, if you set x3 equal to 0, you get that trivial solution. So the trivial solution is included in this general form. And okay, so we're going to do another example, another exercise in another video. So there's another part to this section.